Good afternoon, this is Ray, and I'm ready if anyone is ready to watch. And I think I will start by switching from me to showing the computer screen with the EV program running. You can see we have nothing on the screen. I would like to use some of these features over on the right, but they don't work without a file name. So I'm going to tell it to save this file with an assembly name. Let's call it regs.asm. Right now it knows about the type of file that I have, and if I click CN, you can see that it has placed some code on the screen. I don't really necessarily want that code, but it placed some code on the screen that does the the assembly equivalent of CN, which is to read some data, and C out to print some data, which I don't really want to do that today either. All right, but what I would like is to go down further, and this one says main. We've got a program. Let's see if it works. We'll put a breakpoint on main and click on the green alien. And yes, it's now doing a breakpoint, but it's done the breakpoint on line 10. GDB under Linux is not happy trying to interrupt these instructions at the start of a function. These two instructions are pretty much standard procedure. They, along with the call to the function, will end up with two quad words placed on the stack. There will be the return address and the former value of RBP on the stack. And that will be the stack frame for the function which called main. Here we're setting up a stack frame for main. And when you click on this main icon over here in this template toolbar, it also gives you some information about which functions which parameters go in which registers for parameters to functions. So push RBP, move RBP, RSP, which moves the stack pointer into the base pointer. Those two set up a stack frame. The leave instruction undoes the effect of those two instructions. Now, to see what's happening with the program today, we'll need to look at some registers. So I'll tell it view registers, and it's showing the registers on the screen. I'll slide it over so that hopefully we can see this while we're running a program. So if I tell it to run again, well, let's do the leave instruction and monitor what happens to the stack pointer. Stack pointer and RBP each have something ending in EA50 at this point. So let's see the effect of leave. Aha! RBP becomes 0, and RSP is a number ending in EA58. And if we tell it to execute the return, it returns from the function, and it's no longer debugging this program. What I'd like to do today is investigate doing things with registers and not much more, though I will stop and answer questions if people have any questions. I don't know how to enable the Q&A. The feature is disabled, and I thought it was supposed to be enabled. Well, if you have a question, then you can use the chat, or if you're live, then you can use your voice to speak. And I think Paul is the only person who is on this session live. Now, in order to do something with registers, we need to use the move instruction, which is MOV. So let's move the number 0x, and that ought to be enough else, I think. Move that into RAX. So now it's stopped at the move instruction. You can see RAX has 400C00. Execute the instruction, and we get that. Let's make it a little bit bigger. That may be enough. Let's see how many we get this time. Oh, does not fit in 64-bit fields. I got too many of them. I didn't count. That looks like a good number. Let's try again. All right, I don't know how many I've got, but I've got more F's than before. And you can see now we have all those F's in there. This is not extremely exciting, but let's add some more code. I think I'll tell it to stop on this. And then, hello, Glenn.
Hello. Hi, how's everything?
Going well. How about you?
Well, just a little bit.
Your speech is kind of broken up a little bit.
It's probably because I'm trying to get through the live proof case.
All right.
And get on through the laptop. I hear you pretty well, and that's important.
So that we have two instructions to move things. We've got move a bunch of F's into RAX, and then we've got move into EAX. So what happens with that? All right, we got our F's in there. Looks like there might be room for one more F. All right. Now, after we do move into EAX 1, 2, 3, 4, we see we've got 0x 1, 2, 3, 4 in RAX. So the effect of moving into RAX is to move a 64-bit quantity into RAX. The move into EAX is to move into the 32-bit half of RAX. And when you do that, it automatically zeroes out the remainder of the register. Let's do a little more. How about moving into AX? All right, so we do move with the big number. So we got a big number into RAX to move with the AX, and we get 1, 2, 3, 4 in there, which clears out the top half. And when we move the 2, 6 in there, we get just 2, 6. All right, let's try one more. Move AL. How much more fun can there be? So we can move constants into registers. Can you move registers into constants? No. All right. So let's get rid of line 11. Oops. The alignment doesn't matter, but it bothers my sensibility to have the code look rather goofy. All right, now we're going to move the big number into RAX and then move a 26 into AX. Oh, that's interesting, isn't it? So when we move into EAX, it zeroes out the top half of RAX. When we move into AX, it doesn't. And then when we move the 12 in there, it wipes out the top half of AX, but it doesn't wipe out the low half. I guess we can do one more move. Oh, I don't want uppercase. It's probably happy with uppercase, but I'm not. AH. Move a 5 into AH. All right, so we get the 1A in the low part of the number. And then this is interesting. So notice that the number of F's we have here is moderately large. We've got the first or the top 3/4 of the register are remaining the same when we move with AX, AL, and AH. So those are a little different. RAX and EAX wipe out the whole register or replace everything in the register. The value of using EAX is it uses fewer bytes for the instruction to do that. All right, so let's wipe out some code here. And let's add some data to the program.
Hey, Dr. Sayforth, is the length difference between RAX and EAX, is that because RAX is like doing two instructions, clearing the register and then moving data, and EAX is just...
RAX is the name of the 64-bit register. EAX is the name of the 32-bit register.
Gotcha.
They're physically the same. The EAX is the lower 32 bits of the RAX register. And the way that it behaves is for convenience. If you're moving something into EAX, you're using fewer bytes, and it makes it convenient to write your code. You use up fewer bytes for your instruction space if you can use a 32-bit quantity to move it into a register. So something like moving a 5 into EAX is the same logically as moving 5 into RAX, but it takes 32 bits less memory to do it. That make
Gotcha.
sense?
Yeah, perfect sense. Thank you.
All right. We have completion. What knows about data, and I'm going to use A as one of my favorite names for a variable. And let's see, DQ for a quad word number. And let's put a 5 in, 5 into A. What's going to happen here? If I move A into RAX. So you want to know what I will get?
Is RAX a purpose register or an address-specific register?
It's just a register. Registers can hold addresses or numbers.
All
right, so here we are ready to do it. Will we get the 5 or something else? And the answer is we get something else. So what is 0x602088?
Is it the memory address where A is stored?
That's correct. So if you want to get the address of A, you need the load effective address instruction. And you're supposed to use LEA. Now this works, you get the same thing with each of these. So let's do this way, and we get the same thing from the next instruction. If you want to get the value of A, the thing you need is brackets surrounding the variable name. So now if we run this, we execute the move with the brackets around A, we get the 5, then we do load effective address, we get this. Interestingly, the move instruction generally is restricted to 32 bits for the field of the instruction. I think there may be some circumstances, like if you give it a 64-bit explicit constant, you can move it into a register, but in this case, that move is a 32-bit number. And it works with Linux because the data segment and the text segment are both within the first 4 gigabytes of memory. So the address fits in a 32-bit number. This is not true with OS X. So if you're running with OS X and you try to move A, and not with the brackets, but move A into RAX, the assembler will tell you that that's dumb. It won't assemble that. You have to use load effective address to get a 64-bit quantity for an address into a register on OS X. Under Linux, you can do it either way, either move the variable or load effective address. And I recommend I recommend using the portable instruction, though it hardly matters much. If you didn't do that, then you could stand a pretty good chance of writing portable code between OS X and Linux. Are there questions? All right. So if we put another variable in here, supposed to be ABC. I can't spell. All right. So what is the address of B if A is at 602.088?
Presumably that plus 64.
Plus 8, because it's counting in terms of bytes.
Gotcha.
You got the right idea. Oops, can't type. Load effective address, let's put B into RAX. So we get first instruction, we're going to move B into it. And then we'll move A into it. Let's make it a little more logical. Let's move B into RBX. What a clever plan. So now we can see that, sure enough, that's 8 different. And if we go over to here, and I've got my cursor on RAX, you can see a little blue stuff on the screen. And if I click on right click, maybe I can do a right click, let's see. All right, if I do right click on that part, it says define a variable with this address. Finally got it to work. I'm trying to use 2 fingers to simulate a right click on my touchpad on my fancy keyboard. For all these registers, we get the choice of using either decimal or hexadecimal. And you can do them all at once if you want, though decimal is not really that advantageous for addresses in case there was any difficulty seeing what difference was between those. It's a difference of 8. All right, so we can view the registers. Now, what else can we do? I've got small difficulties.
You could probably control minus and drop your text size if you were looking to put more on the screen.
Well, is it very visible or is it?
I don't know about the other guys. I know it is to me.
Pretty visible?
It looks fine on mine as well.
All right, let's move RCX. And we'll move A into RCX. And then I'm going to do one more trick. Move A plus 8. So we have B's address, A's address, the value of A, and then what are we going to get when we move A plus 8 instead of A? We're specifying an address that is at essentially the same as B, right? And what do we get for B? Well, we only specified 3 bytes, but we moved 8 bytes. We can be assured that there are whole pages of memory mapped at a time, so we could go well beyond the values of B. But you can see that we have this, of course, is backwards. The memory is stored. A is the least order byte of this value, and then B, 6.1 is a lowercase a, 6.2 is a lowercase b, and 6.3 is a lowercase c. And then the rest of it is 0. Now, if we wanted to explicitly put a 0, we need to do this, right? It had a 0 out there anyway, but let's do 1, 2, 3, excuse me. Now we've got a total of 8 bytes defined. All right, we get the 5, and then A plus 8. We get A, B, C, and then that 0 byte, and then 1, 2, 3, 4. It can't be much plainer than that, can it?
Doesn't seem likely.
Let's move. How about if we move like this? Does that have the window on the screen with the error code?
It does.
Okay, so it's not happy with that. And the answer is, whenever we're doing things with a memory address that is like A or B or something, then we need to put it in brackets to use it as an address to reference a memory. So if we do this instruction, all right, we're ready to move it into A. Now, how do we know that it's in A? I'm going to view the data now, and let's see. Got them stacked, so I can switch to the data and switch back to the register. If we do a right click on this, it says define a variable with this address. And I will conveniently call it A. The address is a constant. The type, I guess a long would be good. How about an unsigned long? All right, so at this point we've defined it, and we've got the value that was moved from RCX into the address of A, right? So that shows that we've changed memory. After defining that, if we run the program again, then we have 5 in A, and it'll remain in A until we execute this move instruction, which changes it. So we've seen a little use for the data window in EV. Right click here, we can edit the variable or delete the variable. So if we edit it, not too much excitement here. We can convert it to decimal or binary. There's not much else we can do with it. We could call it an array variable and tell it that it is an unsigned character. Tell it that it has 0 through 7, and I think this will work. Let's see. That was not the way it should have behaved. All right, so now we've got some goofy looking characters. Let's display these as characters. We got ABC, the 0 showing up as a triangle pointing up. And then we get some other characters that I haven't seen before. What more is there to know about the move command? You can move from register to register.
If I recall correctly, you cannot move from memory address to memory address, however, correct?
Not the move instruction.
Right.
Better use CX. All right. So along the way here, we will be looking at a move from RCX to RDX. All right, and you can see that works. There's nothing more involved with moves. Let's see, there is a bunch of instructions that are called string instructions, which can do things like move a string of bytes, and it can move a sequence of bytes from one memory location to another memory location. That's the only thing that I'm aware of that moves from memory to memory. All right. Do we have some questions about any of this?
Yeah, the string operations, is it just like niceties where it, instead of having to write like 3 instructions to move from memory to register and register back to a new memory location, it just does that all for you? Or is that actually like a single instruction on the
Well,
CPU?
you have to set it up. The string instructions use registers RSI and RDI. The S for source, the D for destination, and it will move a byte or whatever quantity you want to move from the source, the RSI, to the destination RDI. So if you set up RSI and RDI, you can do a handful of different choices. There's some scan choices that'll look for things. You can load one byte, inspect it, and optionally move that byte to the destination. So you could go through and strip out all the carriage returns, let's say, from an array of characters.
As I recall, you're setting up basically a stream, and RSI being the source, RDI being the destination. You're saying take
right, and when you load something, you use
this byte
RSI
here to here, and then advance the counter.
Yeah, so you can specify a counter and tell it to repeat it, or you can just do like the LODSB instruction and load one of them at a time without the repeat instruction involved with it. So if you did that, you move one byte into there, and then you can inspect it, and it will automatically advance to the next one, so you can write shorter loops to do that kind of stuff.
Are you still there? Things kind of went silent.
You don't hear me?
Oh, now I can.
Well, I didn't mean to be too silent. All right, all the registers except for RBP and RSP are general purpose registers. I've clicked on the wrong window. All right, so if I switch to here, I clicked on registers. Well, I'm going to move this thing back to the bottom.
Sorry guys, I gotta drop off my moving madness here.
All right.
All right,
Catch you later. Nice chatting with you, Paul.
yeah, absolutely.
All right, so all these registers are somewhat similar. RSP and RBP, you can do any of the instructions with those, but RSP is the only register that works with the push and pop instructions, right? And RBP is used as a base pointer for stack frames, but it doesn't have any explicit specialness. So all the registers are general purpose except for RBP and RSP, and except for RSI and RDI being source and destination. And one more thing, when you when you're using those string instructions, they operate with RAX. So if you move a byte with the load SB instruction, the byte will go into the AL register, the low order byte of it. You can do moves of words and it'll go into AX, or double words and it'll go into EAX, or quad words and it'll go into RAX. The registers are general purpose. Yes?
I'm sorry, it just has to do with the initial AX accumulator.
Yeah. It was an accumulator.
The original.
And C was a count. I don't remember what was special about RBX and RDX, but not a whole lot. And then when they invented 8 new ones, they finally wised up and used numbers. I briefly tried to figure out a way I could conveniently number the registers so that every register could have a number, but RVP and RSP are a little bit special, and if you number the registers RSI and RDI, well, they're special. Then need to know which number meant source and which meant destination. It's ugly, but what are you going to do? You could do something to change with macros so that you have R0 is the same as perhaps REX, but it's not that pretty. All right. Do we have other questions about moves or registers? All right, let's wipe some stuff out here and make it do something more realistic. We'll define B to be a quad word and give it the value 10, and C will give the value 0. All right, so my goal will be to add A and B. All right, to add A and B, we get several choices of what we could do, and my choice will be to add B directly. You could move B into a register, or you can add it directly. Where my cursor went. So we get A into REX, and then we add, and once again we use the bracket surrounding B. At least it's consistent. And 15 is an F in hexadecimal, so that's fine. And then we would like to save the result, and we'll put that in C. So we'll start it up. And we could define a variable for C. I don't have an address convenient here. The assembler knows a little bit about variables, but doesn't know a whole lot. All right. So let's highlight C. And we can right click over here. It says define variable. And it says C is the name, the address of C is the address. And it's a quad word thing or a long as far as C++ is concerned, or C. So let's leave it in hexadecimal, do it OK. Oh, we've got 0xF. Now the difference between what we did earlier and this is that this time the address is &C as opposed to being 0x600, whatever it would be. Right? So there's two ways we can define variables for use in assembly. If you're doing this in C or C++, local variables would have a complete definition to the program. In assembly, the program knows about the address of A, B, and C. It has no clue about the type, the debugger, that is. The type could be a float. The type could be two floats in an array. Who knows? So we have to define the type and the format for it. We have so many choices. All right. I will digress slightly so that we can illustrate a little bit of the joy of this thing. If you want to output something and you're not used to doing it in assembly language, I clicked on the cout icon on the right, and it put this code into my program. Defined a format string. Let's see, I'm going to get rid of this data display. Format string saying like percent, or excuse me, I equals %D, or I is %D. And, oh, this is bad. I need to fix that. Supposed to be a comma there. I've got a period. This hasn't been tested. All right, so if we're going to do this, let's see if we can make it work. Let's give it I and see how good the code is other than that period. Oh, printf. It doesn't know about printf. You have to tell it that printf is something that you're not going to define. It's supposed to get from a library. So we put extern printf. And I think that'll do the trick. Is it extern or global? Oh, it's global says we're making something global. Extern says we want to use something that's global. Let's see if this is right. Aha. So now we do loading into RDI of format. RDI is the first parameter for a function, and RSI is the second parameter. Yes?
I can come back later. I was really not sorry.
Okay. Let me mute this. All right, I'm going to have to join you guys in a few minutes.
All right. So we've got two parameters to printf, and if you're doing it in C, it would be printf and then open parentheses and the string with I is %D and a \n is 0. And then after the string, a comma and I. Doing it in assembly, you have to put the format string's address in RDI and the value of I into RSI, the second parameter. There's one more bit of fun with using printf. You've got to tell it that you are not using any floating point parameters. With printf, you could be printing floats or doubles, and in that case, printf needs to know how many there are so that it can properly manage the variable number of arguments. So here we have XOR, EAX, EAX. What that does is it zeroes out RAX. So if we got 64 hexadecimal or 100, and then you can see we got 0 for RAX. Exclusive OR gives you 0 where the two values are both the same. So it's essentially like a not equals instruction. If you do XOR EAX, comma EAX, it is like an assembly idiom for zeroing out a register. Then we call printf, and I'm going to do this one instead of the one to the right. The one to the right would step into the printf code. This one executes it, and we need to view the data. Excuse me, the terminal. So here we have the terminal. It says I is 100. So now we have something that prints, and I will try to get that period replaced in my code. All right. Going a little further down in this collection, we have a handful of other things. This thing that has a red box is some code that you could either go through and execute the code in the box or not. So that's an if. And I won't explain everything in here, but if REX is greater than 5, then that translates to these instructions. Do whatever you want to do in the body of the if, and then a label for where you go to if the REX is not greater than 5. You'll note that I use JNG, jump not greater than, because here I see greater than, here I see not greater than. It keeps my brain a little bit clearer seeing the opposite in there as opposed to translating it to jump LE, JLE, jump less than or equal. Jump not greater than, to me, looks like it resembles that a little more. All right. I've whacked out the I and all that stuff. This one does an if with an else. I got, again, if REX is greater than 5, and then the else. So if you're doing that, you have to jump not or greater than to else, and then you have to jump past the else clause when you finish this part that is the if clause. This is my crazy notation for a switch statement. So I've got switch code here, so you get the value into a register, and then you compare that value against case 1, compare it against 1, and then compare it against 2, and then you just keep doing that as many as you need. And I've got some code here that is a little useful if you're trying to do a loop. Here's a translation of a for loop. Not going to explain that. Translation of a while loop. And a translation of a do while loop. So if you've got a do, And a while down here, this is a simpler bit of code than the other one. You put the test down at the bottom and jump back to the top of it. I've got a little bit of code here for defining a variable. So the first thing for a variable is 0.5, meaning if you want a floating point number, what do? So you do something with a floating point value. Or if it's in the BSS segment, that is memory that is not initialized in your program. It's part of the data segment. Physically, the data segment consists of initialized data like EQ5 or something, and after that is some data that's just reserved, and you have to put values in it when you run the program. And I've got integer definitions. Here I put for the BSS segment, RESD, you'll note it has a 10 here to remind you that you're reserving a number of memory locations. This RESQ1 reserves 1 quad word. This reserves 10 double words. I want to put some character data in, a string. That's what the ABC means. You've got to put in the string itself in quotes, but you can't use \n or \t or \r, whatever that's in C. You have to explicitly tell it. If you want to put a nearline character, unfortunately, you got to remember 0A, hexadecimal value, or a 10 decimal, and you got to put in a 0 byte, because it doesn't add a 0 at the end of hello world just because it ends a string. It's not a C string. If you're doing that in the BSS, which has the crazy name bulk started by symbol, I don't have any idea why that ever made any sense, but that's what it came from. You're reserving, in this case, 80 bytes. And we started the code with main, and this one, it looks like a graph, is a function. So for a function, I have int f of x, and then in the text segment, I've got elf, the function itself, and I put quotes around this. I think I got the function in there twice. The standard stuff for setting up the stack frame for the function, and when you return from function, the return value is in register REX, and if you're just going to return a 0, oh, this is an error. Got to have 2 values to do an XOR. I assume somebody would eventually catch that if I didn't catch it. If you catch some garbage like this in my code, please email me and I'll try to straighten it out. All right, so functions, this piece of code here with the gears is for a struct. And the one that's a little more sophisticated looking is for a class. Oh, this one's for a class. I can't remember what the difference is. This one is just a group of data. This one with the gears in it is data plus some things to work on the data. So for just a struct, assembly has a struct instruction that defines something that has pieces in it. We'll get to eventually. And if you're trying to do a class, you'd want to have functions. And I defined a struct that could potentially hold 2 function addresses. But you'd have to initialize them yourself. The last little bit here. All right, so now we see the beginning of this library. This hasn't really made it too far into existence yet, but If we're doing assembly, if we go to the top, we can see other stuff a little bit on the other languages. But if you're doing assembly, the code is different with Linux and Windows, though Macintosh is the same as Linux. Let's see, I should have had Mac in there someplace. Macros and the registers are the same. If you want to define a register or macro, you can look at this code. If you want to just look at some assembly stuff, I've got some code in here about defining various constants, data definitions, functions, and I have a little trouble remembering return values and registers that are function parameters. Okay, that's on the screen. It doesn't show the border of this window, but it's up there. All right. I don't know if you're seeing the border of the window or not, but I'm not in the display on my computer. So if you wanted to plug this into your code, when you have it up here, you can go into your code and it's already done the copy part. Just do a Control V. So this is a comment that tells you that the first parameter in a function is RDI, the second RSI, and you can get up to 6 of them with Linux and OS X. And you can have 8 floating point registers in the floating point registers XMM0 through XMM7. If you've got more function or parameters to functions than that, you need to use a stack. And so far, I don't think I've written a function that uses more than 6 parameters, though I should just for drill. All right, so that concludes the discussion of the template code on here. It's probably enough for one day. My voice is starting to get tired. All right.
Okay, Dr. Seifert?
You can just call me Dr. Ray if you wish.
Dr. Ray, okay. Let's see, since I'm sort of really still new at this, of course, a lot of this goes over my head and I'm just trying to absorb it. I just made an effort to install EB a little while before getting on here and ran into some trouble, although I'm reading through the README file you have here, some caveats about installing Qt, making sure that I do that. So I'm going to tinker with that a little bit and make sure I get myself back up to speed on that. Wonder if you have any prep advice for next week, homework type stuff.
Well, my
I'll,
goal
of course,
today was
to
to show a little bit more of EB and to describe how to define simple data and how to move values from register to register, from register to memory, and memory to register. And I suppose the next thing that would be important to look at might be, it seems like it's about time for the chapter that's titled A Little More Math or A Little Bit of Math or something. So that chapter is pretty good. Somewhere fairly early, there needs to be a discussion of memory mapping. I don't know how much people are going to want to see that on the internet, but send questions.
Okay.
I don't
Okay.
really care what I talk about.
Okay. Cool. I'll look at that chapter, a little bit of math, and I'll have that EB. I'll have played with it a little bit by then, so a little more familiar with the tools you're describing. The tools, yeah.
All right. I think you're from South Carolina. Is that right?
North Carolina. Yep. Mm-hmm.
What kind of background is the name KIF?
Oh yeah. Well, that's from Dad's hippie days. But I'm originally from Texas, and right on the border there in El Paso. and so I've only
It's
been
not a
out
normal
here.
Texas name, is it?
No, it's not. It's an Arabic word as far as I understand it, but it has it's got an entry in the Webster's dictionary, so I guess it has some connotations of euphoria or something of that sort. So
Good name for a hippie, I suppose.
right.
All right. Well, I think I'm gonna cancel the talking so I can rest my voice.
Okay.
Talk for an hour.
Yeah.
All right.
Thank
See you later, Kiff.
Okay.
Bye.
Thank you. Bye bye.